Hello and welcome to this presentation related to our Applied Maths unit. Here we're going to review past paper from January 2018. This is revision week 7 and this is essentially a self-study week. Here's an overview of the paper's contents. Question 1 has a fluid mechanics context. It requires the use of the continuity equation A1V1 equals to A2V2. And the solution requires transposition and evaluation of equations. Question 2, context here is a mass spring system, moving with simple harmonic motion. Question requires sketching and plotting of an equation involving trigonometric and exponential functions. Question 3 relates to a 3-section steel tube, calculating areas and volumes. To do this we have to generate and evaluate equations and also refer to the use of similar triangles. Question 4. Context relates to 2 poles and a cable between the poles on a hilltop. Solution requires differentiation to find turning points and integration to find the area. Question 5 relates to a linkage mechanism, 3-bar chain. This requires to show a proof and generation and evaluation of formulae, within which will require the use of the sine rule. Question 6, the thermodynamics context related to a water tank requires solution of a given second order differential equation and solution of an exponential equation. Finally, question 7, kinematics context of a parachutist jumping from a plane. This requires use of equations of motion from our standard formula booklet and solving linear partial fractions, which are then integrated. And here are the approximate start times related to the various questions contained within the presentation, should you want to directly review a specific solution to a question. But please note all times are rounded to the nearest minute. Introduction. This Level 3 programme relates to some quite difficult exam papers for technician engineering students. This whole course of applied engineering mathematics is essentially related to direct entry to university from Level 3. So the academic level of the papers tends towards A-level or further A-level maths. All questions are contextualised, which adds to the difficulty of the paper for some students. Papers generally require proficient understanding of algebraic transposition, the rearranging of equations. That's a prominent feature of many of the questions and is an area that technician engineering students sometimes struggle with. Here's an overview of the presentation. So essentially the questions are briefly outlined and solutions to each of the questions are included. All solutions show detailed steps involved in an attempt to help aid your understanding. I'll only briefly overview these solutions because essentially they're left for students to review at their own pace. As I say, the solutions are very laboured to try and highlight all the steps involved as the solution unfolds. So let's very briefly overview the questions. This is question 1. It relates to a circular pipe shown in figure 1 here, where the diameter varies from D1 to D2, and we have velocity V1 and velocity V2. Obviously the context here relates to fluid mechanics, and they've given us a formula here related to the volumetric flow rate. They've used symbol uppercase V is equal to this expression shown here. Question 1 continues. So here's the first part of the question. When the water volume flow rate remains constant along the pipe shown in figure 1 on the previous slide, we've got to prove the equation that V2 is equal to V1 multiplied by, in the bracket, D1 divided by D2 all squared. Now, a hint shown here is that we need to apply the continuity principle. This again relates to the fluid mechanics context. So the continuity principle assumes the volumetric flow rate will be the same through both position 1 on the left hand side of the pipe and position 2 on the right hand side. So from continuity, the area at position 1 multiplied by the velocity at position 1 is equal to the area at position 2 multiplied by the velocity at position 2, shown here and here. So this is the equation we essentially have to rearrange to find V2 as the subject of the equation shown above. If you think you can transpose the equation A1V1 equals to A2V2 to prove this equation in question 1 part 1, then I'd encourage you to stop the presentation and do so, but I'll show you the full work solution on the following slide. So here's question 1 part 1 and the solution shown here related to the transposition. Notice for the area A1 shown here, I'm using the formula pi d1 squared divided by 4 because essentially the answer I'm trying to prove is in terms of diameter. I've used uppercase D for diameter within the solution shown here. Here's question 1. Now relates to a dam constructed at the end of a reservoir. The water from the dam flows through a circular downpipe, 1 meter diameter. So part 2, we're informed that the water flows from the dam through the downpipe at a rate of 15 meters per second. We've got to calculate the rate V in meters per second at which the water flows through the feed pipe and enters the turbine, shown at the bottom of the sketch here in figure 2. As a hint here, we need to use the equation derived in part 1, shown here for reference, to calculate V2. This is essentially an evaluation problem. The solution to part 2 is shown on the following slide. So question 1, part 2, here's the solution. Given the information in the question, V2 is equal to 60 meters per second. Here's question 1, part 3. We're given the formula here for velocity is equal to the square root of 2 multiplied by g multiplied by h. Using the value of v found in part 2, we've got to calculate the value of h. So essentially we're going to transpose this formula for h. Again, the full solution is shown on the following slide. So question 1, part 3, here's the full solution for the transposition to calculate the height h, shown here in figure 2. Here's question 1, part 4. We're informed that when the volume flow rate of water entering the turbine is capital V, meters cubed per second, the corresponding mass flow rate, symbol Q, in kilograms per second, is calculated from Q is equal to 1000 V. We've got to calculate the values of V and Q. So just as a hint here, note that the volumetric flow rate in the question is stated as capital V, and the mass flow rate is capital Q. But the conventional symbols used within fluid mechanics for these properties is actually mass flow rate shown as m dot and volumetric flow rate shown as q dot. As purely for reference, it's just if you reviewed other material within the topic of continuity, they would most likely use the q dot and m dot as opposed to the symbols used in this paper. But as I said, that's just purely for reference. So we're going to calculate the values of V and Q on the following slide. Question 1 is part 4, the full solution. We calculate V, volumetric flow rate shown here, and then we calculate the mass flow rate, Q, shown here. Question 1, part 5. We're now informed that the power, capital P here in watts, that's produced by the turbine is given by this equation where the symbol eta, Greek symbol, is the efficiency of the turbine. We've got to calculate the efficiency of the turbine given the power produced is 20 megawatts. In other words, we're given capital P and we have to transpose for efficiency eta and of course evaluate. Full solution shown on the following slide. So question 1 part 5, given the equation for power, we transpose it for efficiency, then we insert the numerical values to calculate the efficiency in decimal here and also as a percentage here. Efficiency can be expressed in either form. Here's question 2, relates to a mass supported by an energized coil spring which is fixed securely to an overhead support, or shown in figure 3 here. So of course the context in this particular case is a mass spring system, and essentially we're considering simple harmonic motion, SHM for short. So in the question, we're given the formula for displacement of y, 60 plus 20 multiplied by the sine of 4 pi t. That's displacement of the centre of the mass from the support. And we're informed that time t is measured in seconds. So initially we have to state the technical name for the oscillator movement of this type of system. Question 2, part 1, and of course the type of movement is simple harmonic motion, SHM. And question 2, part 2, we've got to calculate, subpart A here, the frequency of oscillation in cycles per second. So our hint here is from the equation for angular frequency, omega is equal to 2 pi f. We need to transpose to make frequency the subject and evaluate. For your reference, here are typical SHM related equations, and essentially we're trying to calculate the frequency, which is omega divided by 2 pi. Often the equation is stated in the form of omega is equal to 2 pi f. Full solution shown on the following slide. So question 2, part 2, subpart A. So I've transposed the equation from omega equal to 2 pi f for frequency, and I've evaluated the frequency. Note that the omega value of 4 pi is extracted from this equation given in the question. This is sine of omega t in our bracket, and the omega is 4 pi. Question 2, part 2, so question B, we've got to find the period of oscillation in seconds. Again, referring back to our standard equations, the periodic time is actually reciprocal of the frequency. So as we've already calculated the frequency, we can now find the periodic time. So the periodic time, as said, is equal to 1 over the frequency. Frequency is 2 Hertz. So the periodic time is 0.5 seconds. That's the time it takes to do one oscillation. Question 2, part 3. On the grid shown on the right hand side, we're asked to sketch the graph of y is equal to 60 plus 20 sine of 4 pi t between 0 and 1 second. We've got to label the axes. So now we'd have to be aware that we previously calculated the periodic time here, and it takes 0.5 seconds for a complete oscillation. So plotting between 0 and 1 second means we have 2 full oscillations. I'd encourage you to stop the presentation and think how you would sketch the waveform between 0 and 1 seconds for the equation given. Full solution shown on the following slide. So question 2, part 3 here. Noting the periodic time from the previous slide is a half second. Then we have one full oscillation in the 0.5 seconds shown here. And the oscillation occurs about the displacement of 60 millimeters. So effectively the 60 is the average displacement, and the waveform oscillates about this 60. Notice the 20 in the formula is the amplitude of the waveform. It oscillates about the displacement of 60. So the maximum height of the waveform here will be 80, and the lowest or minimum point of the waveform will have a displacement of 40. So that's a sketch of the waveform between 0 and 1 second. Question 2, part 4, subpart A here. We're now given a modified formula that accounts for loss of energy of the spring. So now y is equal to 60 plus the 20, but this time multiplied by e to the negative t, multiplied by sine of 4 pi t. The table below shows some values for t and y. We've got to work out the missing y values. So complete the table. So we need to know what these y values are here in our table. I would encourage you to start the presentation and calculate these values using the above equation. We've now got an exponential function and a sine function to use in the calculation. The full work solution is shown on the following slide. So question 2, part 2, subset A. I've shown here purely for reference one calculation related to time of 0.375 seconds, calculates the 46.25 displacement, and you can work out the other two displacements for the given times. Question 2, part 4, subset B. We've now got to actually plot these values on the grid below and draw a graph. So in question 2, part 3, we have to sketch the graph. Now we have to plot the graph. But it's the graph now of this function here. Again, we're plotting between 0 and 1 second. There's also a sub-question C. Once we've plotted our graph, we have to use the graph in part 4b to estimate the values of t when y is equal to 50. So I'd encourage you to plot the graph and then estimate these values. So I'm going to solve parts B and C simultaneously. Full solution shown on the following slide. Here's question 2, part 4, subpart B and C here. So here's the new graph based on the above equation. Notice in this equation how the exponential function reduces the amplitude with time. And for a displacement of 50, we draw on a horizontal line until it cuts the curve. We find we have two values, time of 0.31 seconds and a time of 0.46 seconds. You'll probably get slightly different values from your graph because we are interpreting the graph here, so we have slight inaccuracies in our drawing. Let's consider now question 3. Here we have a circular steel tube which has 3 sections of uniform wall thickness throughout. Section on the left hand side shown here is 150 millimeters long, outside diameter of 40 millimeters. Section here on the right hand side is 50 millimeters long, outside diameter of 60 millimeters, and a central section joins the other 2 sections, and this is 40 millimeters long. So a 2-dimensional drawing in figure 4 here, and a 3-dimensional view in figure 5. The question suggests we might find it useful to consider the central section of the tube as part of a complete cone. It's obviously a hint to help us with the solution. So part 1, we've got to calculate the outside surface area of the tube, giving the answer to the nearest millimeter squared. Not sure if you want to stop the presentation and attempt this question, but I will show the full root solutions, which commences on the following slide. Here's question 3. Notice for clarity I've labelled the 3 sections now as 1, 2 and 3. So initially we'll calculate the external surface area of section A1. It's purely a tube, so our formula is pi d, the circumference of the tube multiplied by the length. So the outside diameter of section 1 is 40 millimeters, the length is 150 millimeters. So we can calculate the surface area of section 1, and I've done the same here for section 3. Again, this is another tube, but has an outside diameter of 60 millimeters and a length of 50 millimeters. So here's the surface area for section 3. Question 3 continued. Now to find the surface area of section 2, point A2, we're going to use the hint in the question about considering it as part of a cone. So this now requires a knowledge of similar triangles, because to solve this problem we need to calculate the total length of the cone. So using the notation shown in our diagram and the process of similar triangles, we can write x divided by r, shown here, must equal to x plus h divided by capital R. So that's the use of similar triangles, as essentially shown here in this diagram. Here's question 3 continued. I just repeated this formula derived on the previous slide, and now I insert the values into the formula. Lowercase r here is 20 millimeters, dimension h is 40 millimeters, and uppercase R is 30 millimeters. On the next line I simply multiplied throughout by 30 to remove the fractions from both sides of the equation. So 30 divided by 20 is 1.5 on the left hand side, and I essentially remove the bracket on the right hand side. Next line I add x to both sides of the equation, and finally I divide by 0.5 to calculate the value of x, which is 80 millimeters, that's this dimension here. And to find the length of the cone shown in this diagram is calculated by adding the value of x to the value of h. so the length of the cone is 120 millimeters. I should say in the marking scheme there's a slightly more concise solution to finding x, involving slightly less transposition, but I produced this solution before reviewing the marking scheme, so I'll let you look at the marking scheme for the more concise solution. Question 3 solution continued. For reference, here's the solution from the marking scheme, slightly condensed from that on the previous slide. I'll let you review the solution at your own pace. Obviously the answer for x and for the lengths of the cone are the same. Question 3, solution continued. So now we're going to work out the slant lengths of the large cone. I've got it SL here. This would be length SL, which is the length of the cone all squared, plus radius uppercase R shown here, again squared. So we're just essentially using Pythagoras' theorem here. We know two sides of a right angled triangle, we can find the hypotenuse. That evaluates to 123.7 millimeters. Notice R, of course, is half of the 60, so it's 30. Now we calculate the slant lengths of the small cone, SS, so I've labelled it here, and that's essentially this length of the cone. So again, using Pythagoras' theorem, SS is the square root of x squared plus R squared. Evaluating SS is equal to 82.46 millimeters. So to find the frustum surface area of section A2, our actual section, it will be pi r SL, where R is the uppercase R of course, minus pi r SS, little r lowercase here. Let's factor on the pi on the next line for convenience. We can calculate the surface area A2, shown here. Finally, we can determine the total surface area A. It will be A1 plus A2 plus A3. So total surface area calculates to 34,752 millimeters squared. So quite a complicated solution here. I'd encourage you to stop the presentation and review this at your own pace to try and fully understand the process involved in calculating the total surface area. And question 3, part 2, continued. This is a descriptive question. I'll let you review the question, and here's my suggested answer to the question. Question 3, solution continued. This is purely for reference only. This is using the frustum of a cone formula. Allows us to calculate the curved surface area, which is pi multiplied by the slant length L multiplied by the large plus small diameter, all divided by 2. Slant length is calculated here. And given the information in the question, we can calculate the curved surface area of the funnel section, that's A2. And A2 is exactly the same as that we calculated previously using the similar triangles method. 6,477 millimeters squared, and the frustum cone 6,477 millimeters squared, to 4 significant figures. That's purely for reference. Question 4 relates to the calculus. Here 2 vertical poles, height 10 meters, are sited on the side of a hill. 10 meters here for the left hand pole, the right hand pole will be 10 meters. The horizontal distance between the poles is 30 meters, shown here, and a cable is suspended between the poles. This is the cable shown here. Figure 6 shows the 2 poles, the cable and the hillside, and the side of the hill beneath the cable, aligned within a Cartesian coordinate system, x, y. The base of the pole is on the left-hand origin 0, 0. So the cable may be modelled by the equation y is equal to 0.01x squared minus 0.4x plus 10. This is the cable and the cable equation. And the side of the hill may be modelled by the equation y is equal to negative 0.001x squared minus 0.06x. Here's the side of the hill and the equation. Side of the hill is this curve here. So that's the scenario we're given. Question 4, part 1. We're asked to find an equation for h as a function of x, where the function of x defines the vertical height of the cable above the side of the hill. over the range of x from 0 to 30. So again, here's our cable and the equation for the cable, and here's the side of the hill and the equation for the side of the hill. We essentially have to find height h, which means we'll have to calculate this distance from the cable equation. So the red line shown there is the height of the cable above the x-axis, and we'll need to add it to this distance of the hillside below the x-axis. Question 4, part 1 solution, continued here. So essentially to find height h, it's the y dimension of the cable above the x-axis, and because the hillside is below the x-axis, it's a negative value. We effectively have to take away the y value for the hill. And essentially that will mean we will be adding up the two equations, which of course we need to do. Again, here's our y cable equation, and here's our hillside equation. So the cable equation in our formula, then we minus the hillside equation, which of course is negative. So essentially we'll be adding the two equations here to get the overall height h. So h is given by this expression here, and that's this height shown here on our diagram. Question 4, part 2. We now have to calculate the minimum height of the cable above the hillside, and we must show that the answer is indeed a minimum. We're trying to calculate the minimum h value here. So as a hint, we need to differentiate the equation for h, derived in part 1 on the previous slide, differentiating with respect to x. We will then equate the differential to 0 to find our turning point location, from which we can then find the height. But we need to then determine the second differential to check for a maximum or minimum turning point. Obviously we're looking for the minimum turning point here. If you think you can attempt question 4 part 2 without further assistance, I'd encourage you to stop the presentation and do so, but I'll show you the full work solution on the following slide. Here's question 4 part 2 solution. Here's our equation for h. We differentiate the equation with respect to x. We equate it to 0 for a turning point. We rearrange the equation for x, find the location of where the height is at the turning point, put this value back into the equation for the height, which is 7.373 meters, and then we need to check if it is a minimum by finding the second differential. So differentiate the equation again with respect to x. That becomes a positive value, and that relates to then a minimum turning point. So we have a minimum height h. Question 4, this is part 3 now. We're asked to calculate the vertical area between the cable and the hillside. So the hint here is to integrate the equation for h, determined in part 1, to find the area between the cable and the hillside. Again, if you think you can undertake the integration without further assistance, please stop the presentation and do so, but I'll show you the full work solution on the following slide. Here's question 4, part 3, solution. So we're calculating the area under the curve, labelled as A here. So integrating y with respect to x between our limits. So here's the y as a function of x, integrating with respect to x between the limits of 0 and 30. That's the x-axis from 0 to 30. All standard integrals of the form ax to the n. Here's an extract from our formula sheet related to the calculus, showing our standard integration tables. So we'll be referring to some of these standard forms in the following solution. Again, this is all standard form to integrate. I'll let you review the integration process at your own pace. And we just finally insert the limits into the equation and solve for the area. 246 is the final answer. So that completes question 4. Here's question 5. Context here relates to linkage mechanisms. So figure 7 below shows a schematic diagram of a crank and piston mechanism. Figure 7 here is sometimes referred to as a 3-bar chain. Here's the crank, here's the connecting rod, and here's the piston moving horizontally. So as the crank rotates in a circular sense, the connecting rod pushes and pulls the piston, which moves in a linear sense, a translational sense. So we've got gravitational motion into translational motion. I'll let you review the description in the question at your own pace. Just explains what's shown in the diagram. Question 5, here's part 1. We've got to show that the angle alpha, this angle shown here on our diagram, can be of the form sine to the -1, arc sine, inverse sine, r, shown here, the radius of the crank, divided by L, the length of the connecting rod, multiplied by sine theta. Theta is the angle shown here. Our hint in the question is to use the sine rule to find the equation for alpha in terms of r, L, and theta. Here's an extract from our formula sheet, and here's our sine rule that we need to apply to help solve this problem. Again, if you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and do so, but I'll show you the full work solution on the following slide. So question 5, part 1, here's application of the sine rule. We have the sine of alpha divided by the length of the crank. I'm using uppercase R here, they actually use lowercase r in the diagram, is equal to sine of theta divided by connecting rod length. I've used uppercase L. So we can clearly see that we can rearrange to find angle alpha by multiplying by r and taking the inverse sine of both sides of the equation. So here's our solution for alpha, which is essentially the same as that we were asked to prove in the original question. Question 5, solution continued here. Figure 8, shown here, shows velocity vectors P here, Q here, and S, shown here, that are associated with the mechanism. Vector P represents the linear velocity of point B relative to point A. This acts perpendicularly to point AB with a magnitude of omega r, millimeters per second squared. Vector Q represents the velocity of point C relative to point B, and this acts perpendicularly to BC. And vector S represents the velocity of point C relative to point B, and this acts along the axis of the cylinder. Since point A is fixed, the magnitude of S is the absolute linear speed of the piston along the cylinder. Here's point A on our diagram, the center of rotation of the crank. Question 5, continued. So part 2, figure 9 is a diagram showing a closed triangle of vectors P, Q, and S that's associated with figure 8. We're asked to find the 3 internal angles of the triangle in terms of angle alpha and angle theta, and mark them on figure 9. The hint in the question is to determine these 3 angles shown here. I encourage you to stop the presentation and see if you can determine these 3 angles in terms of alpha and theta. So use figure 8 to help you find the angles in figure 9. But I'll show you the angles on the following slide. Here's question 5, part 2. Here's angle theta on our figure 8. Here's angle theta on figure 9. Let's have a right angle between AB and vector P. So this angle here must be 90 degrees minus theta. As this is angle alpha shown here on figure 8. This is angle alpha here on figure 9. So again, we can work out this angle, which must be 90 degrees minus alpha. To find the final angle, we know the 3 internal angles of a triangle add up to 180. So taking the other 2 angles away from 180, we find the third angle is theta plus alpha, this angle here. So there's the 3 internal angles derived in terms of alpha and theta. So question 5, part 3, the magnitudes of vectors P, Q and S are shown here respectively. We've got to derive a formula for S in terms of P, alpha and theta. The hint here in the question is to use the sine rule to find the formula for lengths S. Again, we'll be using a sine rule extracted from our formula sheet. And to derive the final formula, we will also have to make use of the trig identity stated here that can be extracted from our formula sheet. Here's the extract from the formula sheet showing the trig identity we need to use. I would encourage you to start the presentation and attempt question 5 part 3, but the full work solution is shown on the following slide. So question 5 part 3, here's the solution. Here's our sine rule applied, S divided by sine of alpha plus theta, this angle here, is equal to P, shown here, divided by the sine of 90 degrees minus alpha, this angle here. We simply then rearrange for S by multiplying throughout by the sine of alpha plus theta. Then from our formula sheet we use the trig identity cos A is equal to sine of 90 degrees minus A. Of course in this case A is equal to alpha. So we can rewrite the equation as S is equal to P multiplied by the sine of alpha plus theta, but now divided by cos of alpha. So this term here is replaced by this term here. A slight variation is shown on the last line using the notation stated in the question. Question 5 part 4, we're given the value of R, L, angular velocity omega and angle theta. We have to calculate the speed of the piston along the cylinder. So in other words, we have to calculate S. The hint in the question is to first of all find angle alpha and calculate vector P, from which we can then calculate the lengths of line S using the sine rule. Note that angle alpha is calculated from the expression we determined in part 1, and velocity vector P is calculated from the formula P is equal to omega r. In other words, the linear velocity labelled as P here is equal to the angular velocity omega multiplied by the radius or the length of the crank. The full work solution is shown on the following slide. Here's question 5, part 4, begin of the solution. I'm going to let you review this at your own pace. Here's the calculation for angle alpha using the formula we derived previously, noting the relationship V is equal to omega r, then your velocity equals to angular velocity times the radius. In the context of this question, V is actually vector P. We can calculate omega r given the information in the question. So that's the value of P shown here, 10,000 millimeters per second. And question 5, part 4 continued. We now use the sine rule to calculate the value of S. We're referring back to this diagram here within our calculations. Velocity S evaluates to be 7,096 millimeters per second, or approximately 7.1 meters per second. Here's now question 6. This is a thermodynamics context. Water in a tank is heated by a thermostatically controlled immersion element. When the element is switched off on a temperature of T of water in the tank measured in degrees C, it satisfies the equation given here, d2 uppercase t by d lowercase t squared multiplied by the exponential function raised to the power of negative t divided by 10. T represents the time in minutes after the element is switched on, and when the element is switched on, the following conditions apply. At time t is equal to 0, the temperature is equal to 10 degrees C, and the rate of change of temperature with time is equal to 7 degrees C per second. So part 1, starting from d2t by dt squared, is equal to our expression on the right hand side. We've got to show that while the water is being heated, the temperature is equal to 10 plus 70 multiplied by in the bracket 1 minus e raised to the power of negative t divided by 10. This is obviously an integration process, a double integration process to solve the differential equation d2t by dt squared to end up with the equation of t is equal to our expression. I'd encourage you to start the presentation and attempt this question. I'll show you the full work solution on the following slides. So question 6, part 1, is the commencement of the solution. So we've got to solve the second order differential equation by integrating twice. Just written the differential equation here in a slightly different format. Question 6, just note this for reference. The exponential function raised to the power of negative t divided by 10 could be written as the exponential function to the power of negative 0.1t. So in other words, this first term here is in fraction format, but the second term here is in decimal format. Some technician engineering students are more comfortable with the decimal format. We'll let you review the solution at your own pace. We need to integrate twice, so we've got integration the first time here. So that determines d uppercase t by d lowercase t and our constant integration. Integrate for the second time, we now find expression for t, and now we have a c2 constant also. Given our first condition, when t is equal to 0, d uppercase t by d lowercase t is equal to 7, we can find that constant c1 is equal to 0. So here's the solution for our first order differential equation. Question 6, part 1, solution continued. We now impose the second condition. When the time is equal to 0, the temperature is equal to 10 degrees C. This allows us to find constant C2. So ultimately we find our equation for temperature, and to achieve the format given in the question that we're asked to show, I slightly have to manipulate the equation shown here to end up with the final form shown here. So that's the solution to question 6 part 1. Here's question 6 part 2. So using the formula for T derived in part 1, we've got to calculate the maximum theoretical temperature that the water can reach. Our hint in this case is to calculate temperature T using the equation that we derived previously. This is just an evaluation question. Solution shown on the following slide. Question 6 part 2 solution. T evaluates to be 80 degrees C. Question 6, part 3. We're now asked to calculate the time taken after the element is switched on for the temperature of the water to reach 70 degrees C. So it's a hint. We've got to find lowercase t by transposing the equation that we proved, shown here. A more complicated transposition this time, but I encourage you to attempt the question before reviewing the solution on the following slide. Question 6, continued, this is part 3, solution. So we're given this equation, derived on our previous slide. We're informed that the temperature, capital T, is equal to 70 degrees C. We've got to solve for the value of T in the exponent of the exponential term. So essentially we have to rearrange the equation to have the exponential term on one side of the equation and make it positive. That's what's been done here. Then we exponentialize the equation, in other words, take natural logarithms of both sides of the equation. And that then allows us to rearrange algebraically for the value of t, 19.5 minutes. And finally we have question 7. The context here is linear motion, and we'll be referring to Newton's equations of motion. Here's an extract from the formula sheet related to the section entitled kinematics. And here are the equations of motion stated for us with the nomenclature on the left hand side. So part 1, a parachutist jumps from a plane and falls under the influence of gravity until her speed reaches 40 meters per second. That's vertically downward. Assuming that the aerodynamic drag can be neglected while she is falling. We've got to calculate the time taken to reach this speed after jumping from the plane. We're allowed to assume that her initial vertical speed is 0. So the hint for question 7 part 1 is to calculate the time taken using an equation of motion. So an equation from our listing here. The solution is shown on the following slide for your reference. So question 7 part 1, here's the solution. Using this equation from the formula booklet, u is 0 in this case, acceleration is gravitational acceleration. So we can rearrange the equation to find time calculated here. Question 7 part 2. When the parachute's speed is 40 meters per second, she opens the parachute and continues downward for 100 seconds before landing on the ground. From the time when the parachute is first opened to the time she lands on the ground, her vertical speed v meters per second is modelled by the equation shown here, where lowercase t is the time in seconds after the parachute was opened. We've got to show that this expression is true, noting that capital A, capital B are constants to be determined. The hint here is to solve for constants A and B using linear partial fractions. I encourage you to stop the presentation and attempt question 7 part 2, but I'll show you the full work solution on the following slide. So question 7, here's the solution. I'm using the cover-up rule here to determine constants A and B. I'll let you review the solution here at your own pace. The value for constant A is 1 and for constant B is 2. And question 7 part 3. For this part of the question, we're given the following result, where lowercase a, lowercase b, uppercase c are constants. So we've got to use the formula for v, given in part 2, to find the vertical distance, lowercase d, calculated from this integral here, travelled by the parachutist in the 100 seconds that the parachute is open. So essentially this is an integration problem. Question 7, solution continued. This is for part 3. So we now essentially integrate each of the terms on the right hand side between limits of 0 and 100. I'll let you review the solution at your own pace. The final answer of the distance is shown here. And note the integral here and here are solved using the standard form given in the question, shown here. The third integral, of course, is standard form, basically ax to the n format. That's in the standard integral table in the formula sheet. Question 7, part 4. We're asked to calculate the height above the ground at which the parachutist jumped from the plane. Our hint here, to find the total height h above the ground, will require using an equation of motion. But again, back to our extracts from the formula sheet related to Newton's equation of motion, we need to choose the appropriate equation to use. So here's question 7, part 4, solution. I'll let you review this solution at your own pace, but we can ultimately calculate the total height for them. So that concludes the presentation. These questions are very difficult, particularly for technician engineering students. I myself find them challenging, but are also very interesting. I wish you well within the examination.